So I guess, again, just to kind of get the discussion going, yesterday's theme was more algorithms and maybe neuroscience. Today it was a little bit heavier maybe on the hardware implementation, ways to run these things. So maybe, again, just a starting theme, what's your perspective in terms of the tools we have right now, all the neat things we can do with them, and what's next? So, I mean, Karl-Heinz and Steve, with your systems, you guys have described some of the really neat experiments that are sort of coming down the road. But if you kind of project next step 2, 3, where could we go? What are some of the things that we might really be able to get at hand in short order? Short order being kind of 2 years, maybe 5 years.
Not to, I mean, Karl-Heinz and Steve will weigh in on the roadmap for 5 years from now, but just before that, I would say that they've put on the table extraordinary systems to use. Like, the system that Karl-Heinz just described, 10 minutes ago, has so many powerful capabilities, none of which have been explored, except just scratching the surface. And so, what's on my mind is seeing when we can work together to use his systems. And if in the meantime he's planning for something 5 years from now, I'll leave that to him, but I'll be busy during those 5 years using this system he just showed us.
Yeah, so the plan within HBP, as I outlined in the talk, is to produce a second generation machine, but I think it's very important that we get a lot more experience with the current machine. I mean, I showed you the big box of hardware. We don't yet have the software to configure that, and that's coming together now. But we're even more short of models that do something interesting on that, because this is a scale of resource that that people really haven't thought about how they would use if it existed, because it hasn't existed. Mm-hmm. So there's a big sort of pull on the user community to try and come up with challenging models that can exercise these machines that we can learn from, and then we can feed those lessons into the next generation.
So maybe I'll put Nathan on the spot. So what would you guys want to do?
Good question. Yeah, I mean, I think I agree that we probably don't have very firm plans just because that kind of thing hasn't been available yet. I think as we, I mean, the Institute's focus is kind of on what we can do at scale, what we can do with more tractable things. So that kind of our plans are more, what has been available for the last 5 years rather than what's going to be available in the next 5 years. But, as I think we'd like to kind of start, with the visual cortex, but then keep expanding outwards. So as long as we can, potentially we could take advantage of some of this new hardware to, have bigger simulations that we could test their correspondence with hopefully even bigger experimental data sets as well.
I want to add one thing, which is I think someone had a slide about it's all about entertainment, right? and in the sense that we're getting at least this community getting some press from True North, folks seeing it out there and getting that press and people understanding at least what we're doing. I think from the commercial side, NVIDIA pushing a lot of the kind of deep learning on their Tegra and things like that. That's good stuff. Meaning, that brings our work more to the kind of user realm, the real folks out there, and that gives us visibility. I think that's good, and hopefully that drives it as well in terms of funding and what have you. So I think that as a note for us, from a tool perspective, that's going to grow, and that will help.
So I guess I come about it from a different perspective in the sense that, if you think about what Steve and Karl-Heinz talked about, they're going for big systems, right? Whereas I'm interested in how do you get small, right? So how do we basically take the kinds of things that that Karl-Heinz and Steve are doing and make it really small, but yet still be able to do a lot of computation, and then use computation processing methodologies that will allow us to build these sensory integration systems that we talked about yesterday. Being able to have that that drone fly around and not crash into walls and whatnot, and coordinate and so on. So still, another angle of it, but yet I think another valuable angle of it.
I can just name a few specific things that I'd really like to take a look at with the hardware, which would be, let's see, models of dendritic computation, plasticity, mostly with SCDP, and models of homeostasis too. So all those things, I think it'd be really fun to have a piece of hardware that could run these much quicker than our current implementation. And that could, especially because when you're researching plasticity, you kind of have to wait. You can sometimes turn up the learning rate and it helps, but sometimes it's not a good idea. So definitely those aspects I'd like to take a look at.
Well, I mean, sorry, just a word of warning to cool down the enthusiasm. Our system, it's really, you today, Murat, you talked about non-symbolic computing, and that's what it is. It's an event-based, non-symbolic computing device. So it doesn't understand programming language. You cannot deliver a set of C code, other than for the plasticity processor, of course, where you can do it. But otherwise, it's a completely different way of using a computational device. You don't write a program which is being executed. What you do is you define an architecture, connectivity, a set of parameters, and you define maybe rules for plasticity, for rewiring and things like that. And then all you do is to switch the thing on, and then you see what it does. You expose it to data maybe, but it doesn't execute an algorithm. So it's a completely different way of doing computing, and this is why I see that very few people really at the end achieve something with this system at the moment. And this is why, for the time being, it's mostly our own students, because we can torture them locally, telling them what to do and helping them whenever they have problems. So, this is, although we say it's remotely accessible, that's true, you can do it, but it will probably not be very rewarding because you will see lots of failures. That I can tell you, it's hard work to learn how to use these systems. They are unreliable, there are big variations, it has all these analog elements, so it's a completely different way of doing computing. So if you want to do it, and you are very welcome, I suggest that then we torture you first. In our lab, you come and visit us for a couple of weeks, work with us, and then you can go home again and use it from outside. There's one good example where it worked very well. That is Michael Schmucker, who is a neuroscientist who got enthusiastic about neuromorphic computing. He actually spent a couple of months in our lab. He really learned it, and now he can use it from home. I think you have to go through this phase. It's not something where you just, download a little bit of code and then upload it and get the result. It doesn't work like that. It's a completely different way of doing computing. That's just a warning.
Well, shouldn't it?
Well,
It should work like that, right?
Well, actually, I would argue that some of that, I kind of in your court on this. The first thing I was going to say to your comment was, if you're actually curious about how to actually do dendrites and SGP and stuff, we should talk more. Because that was some of what we actually showed a little bit today. So I think those things are actually in play. I actually do think, I actually kind of interesting in the conversation, but I do actually agree that we should make this to be as easy and accessible as possible for people. That is really where the tools come into play. It's also where I think the computational framework conversation comes into play. In other words, what computing actually does this do, and where is it really effective? Where is it actually competitive? I think those things are in play. I do think, though, being realistic, it still takes some time. You'd like to get it down from months to maybe a couple days. Somebody could hang out for a week in a lab with people, and then you have a reasonable kind of network for remote systems and so forth. And I think that's actually is an important challenge, and given that several of us up here are educators, we're probably well equipped to ask those questions, I think.
So when I say something, so it's unfortunate that I think all the funders are gone, right? Because this would be kind of something to sponsor, right? Basically summer schools, and long-term workshops that bring people to use, hardware and so on that are available.
No, that's absolutely true. And that's also on the shopping list of HPP. We have funds just for that purpose. There is an education program. And for example, this this, when is it, late summer, right? There is the computing school of HPP in Austria. This is one occasion, and there will be more events like that.
And of course there are the existing events, Telluride, you've already marketed aggressively today. There's Capocaccia in Europe, which is a kind of similar 2-week workshop where a whole bunch of my students will go and we'll take a lot of Spinnaker stuff and so on. We're sending people to Chris Eliasmith's Nengo workshop in June in Canada. We run training workshops in Manchester for people who want to get introduced to the technology. So, I mean, training's a big deal. But I think the thing I kind of forgot to say in my talk today that I think is really important is the key to finding a sensible use for these big machines is to have some sound underpinning theory from which to build networks, which is one of the reasons why we're so attracted to work with Chris Eliasmith and Nengo, with Jeff and HTM, and Randy O'Reilly's system, because in those cases there are theoretical underpinnings which give you the ability to construct very large, complex networks and expect them to behave in some kind of sensible way. I mean, I don't think any of these theories are perfect in the sense they cover everything, but they're much better than not having any theory at all. I mean, one of my fears in large neural networks is, the PhD topic where the student spends years searching in infinite parameter space for something that kind of happens to work, randomly, and usually you find a set of parameters that kind of do what you're looking for, and you've no idea why, and you've really not learned much. So underpinning theory is the key, I think, to progress.
Okay, let me agitate then. When I was in high school, that was in the 60s, I remember vividly a number of teachers saying, we don't really know what electricity is, which really struck me as a strange statement. I heard several speakers today saying we don't know how a brain works. In detail, that is certainly true, but haven't we reached a point where a lot of the basic principles have become reasonably clear? So isn't it a rather too strong a statement to say we don't know how our brain works?
I would say we know more about electricity.
Yeah, I mean, I think we know a lot about how the brain works. I think the thing that we're all interested in probably is how it does the really complicated things, and specifically how the human brain works. And there I would say that's a lot more fair of a statement. So, we know a lot of the underlying biophysical mechanisms that are involved, but in terms of the, higher level processes, we have lots of theories. We don't have a lot of direct experimental evidence for that. That's also hard to do in human. But yeah, I don't know. I mean, I'm sympathetic to the comment, but I also do realize that, there is, as people keep arguing, there is lots of data out there. There's lots of understanding out there. So maybe it's more of kind of a sociological issue, right? Trying to put that together in a more concerted or useful framework. And that's something we can try to work forward to.
So I would, again, we want to make this interesting and provocative like last night. So I would say that I'd be the first to say that we certainly have a vast amount of granular information about elements of neurons and synapses across brain areas and across phylogeny. But there's been no synthesis, scarcely any synthesis, and really it's profoundly true, embarrassingly, appallingly true, but maybe that'll begin to change now, that we couldn't account for much at the microcircuit level of detail regarding the function of any neural system in any creature, from an insect to, forget about a human, but anything, fish. We can dive into the optic tectum of the fish and talk all day long about how the retina wires to it. And that's, sort of a pillar of knowledge, but to actually account for its function in a mechanistic way via simulation or via an emulation or something like that. And the same goes, so it's really, that's one of the difficulties, the challenges of the field, and we have to turn the corner. And I think the kinds of observational breakthroughs that Jeremy Freeman he's one of the country's leaders in this right at the moment, that are now happening with these new optical methods scaled up to volumes of circuitry being interrogated during sensing. This is revolutionary, and this will give a picture of microcircuit function that we've never had. And I would predict that it really will usher in a new era, but that era hasn't started at all for any creature right now.
So one analogy here is, imagine we're trying to reverse engineer an Apple iPhone. Okay, I think we're at the stage where we've just about worked out what transistors are and how they work, but we've got nowhere near working out that there are numbers represented in binary in there. We don't know how information is represented inside the brain. I kind of reduce this to one of the questions is you look at the flow of information from a sort of sensory input through a layer of cortex, and the question is what's the value added of that layer of cortex? Why is the information that comes out of it better than the information that went into it? Why is biology spending all that energy doing that processing? How do we work out if it's getting good value for that layer of cortex? How do we measure its energy efficiency? We just don't know how to do that, how information is represented, how it's stored. So we haven't worked out yet that our smartphone actually has got binary numbers, and nor have we spotted where the adders are. And we're a long way off understanding, the microarchitecture and where's the level 1 cache. We just don't know what the terminology is to describe those levels.
I think to answer some of the question is, as long as you get to an abstraction where you can make some usefulness of it, whether correct or not, and you evolve from it, right? So, it may not be the right answer, might not be the right model even, and we'll find out more as new tools and things are capable. But at least you get to an abstraction that says, this is workable, you build new systems out of it, demonstrate it, and then evolve from there. I think that's as important as saying, getting the right answer. I think that's some of the things covered yesterday as well.
So could I extend Dr. Ferber's analogy? I'd like to extend your analogy. In the case of us trying to crack the Apple iPhone, if we went in with the knowledge of the theory of computation, an understanding of digital logic and algorithms, then we would much more quickly derive what those different components are on that circuitry than if we don't have that theory. We worked out what the transistors are. If we also had the theory, we could fill in the middle pretty quickly. I think what we kind of lack for our understanding of the brain is a larger theory. Now, we come up with a lot of ideas and they get bandied around a lot, hierarchy and sparse representation, all that kind of stuff, but they feel to me like stuff we pulled out of our navel. They're kind of intuitionistic. And it may be that we'll just have to keep guessing until we hit the right theory and then things will fall together. I tend to be an extreme bottom-up mentalist because I'm hoping that by putting molecules together we'll eventually figure out what the theory is. But
It's a long way.
Yeah.
So I guess there's a few people who've been thinking about, the brain as one big Bayesian inference engine, right? So, and there's a lot of description of various parts of the brain. Take the motion estimation area MT. You look at the work of Eros Amicelli. I mean, he's definitely described a lot of what happens there in terms of Bayesian inference. So, and then there are folks who think about it that way. So, I guess should we be looking for a grand unified theory that pulls all of it together and says this is the string theory of the brain kind of thing?
I think we need to be careful about how we can even falsify a theory like that. Because let's say you have a theory and then you apply some tests and it doesn't work. And then somebody says, oh, but you have learning and you didn't account for learning too. So that's why the theory didn't work. You didn't have the right predictions because you didn't have the right learning. So it might be that in order to test any small part of the theory, you need to have a good big part of the theory too.
I fully agree that being able to falsify theory is extremely important. I mean, that's part of the reason why theoretical physics has been so successful. I mean, there are many, many theories that have been generated in the past which by experimental observation just failed. I mean, it's just the position of the sun in the universe, for example, is with a few simple observations you can see that the Earth, for example, is not in the center of the planetary system. So that's something which is really based on observation. So there are good and attractive theories, but they just do not agree in all detail with the observation. This is something we have to do. Now the question is, which observations can we make? The biological brains are not so easily accessible. I mean, there are these wonderful new optical methods. They will help us. But I strongly believe that also synthetic systems will help us to falsify or verify or at least support theories. And by synthetic systems, I mean both. I mean, it's very large-scale simulations. And of course, coming from the Human Brain Project, I have to say this, but I also believe that large-scale brain simulations have a role in uncovering how the brain works and how information is processed. And also simulations that go to incredible detail of neural cells. What we need is a systematic way to do very detailed simulations that really represent a huge fraction of our biological knowledge, and then in a very systematic way take out complexity, simplify the system, and see where certain computational properties disappear. And it's that pathway which I think we have to walk on. This is one of the main plans for the Human Brain Project, to do exactly that.
I'm glad you used the word "I believe." In order to falsify a theory, you already have to have a belief system. That puts a big dent into falsifiability. It's not so much, the science is objectively existing in a vacuum. Science is scientists, and they are a rowdy bunch. They hold different kind of beliefs.
I believe in spikes.
So I have a question more as a hardware designer. You're talking about the theories and what abstractions are necessary and at what abstractions we can build these systems. So recently I came across a research article from researchers from UCLA who said the memory is not in the synapse, but it is in the nucleus of the neuron. So this is a pretty, they're still not conclusive on this results, but when I as a hardware designer read something like this, it is a radically different approach to what I'm believing in and applying or designing the system. So how should hardware designers take existing theories, or is there like a compilation that neuroscientists could help us that these are accepted, or these are fundamental theories that you could build your systems on?
So not to be flippant, in that particular example, you should remember to not believe everything that you read. More so than in circuit engineering, the biological elements are complex, and the experiments are. You have to read the literature broadly enough to be able to assess a statement like the memory, synaptic memory resides in the nucleus. I mean, certainly there's expression of synaptic change is a very complicated system. It involves protein production. It involves activation of genes in the nucleus, and there's transmission from synapses to the nucleus and back. So the nucleus is somewhat involved. But on the other hand, I think if you had the time to read more of that literature, you'd begin to see that you would put that paper in context.
Perhaps I gave an extreme example, like even I think the role of dendrites, I think, is more discussed in this workshop than probably the previous year, like how they're useful in active computation, and depending on the distance from the, I think the neuron, how they play a role. And I think a lot of these things are really not implemented in the abstractions we are looking at right now, because we are not mimicking these systems, and we do not know how important these things are. So
that particular topic has been the focus of my research through my whole career, the active dendrites and their functional implications and their role in computation. So I can quickly say that there is, in the last 15 years, there's direct experimental evidence, recordings of dendrites that show straightforwardly that they're highly nonlinear and full of active channels that are voltage gated. And they have all kinds of consequences without any doubt: spiking in the branches that doesn't propagate to the cell body, propagation of cell bodies firing outward to the tips of all the branches. All of these have pretty self-evident computational implications. You can't really imagine a neuron being properly modeled if the dendrites instead are passive, if in reality they're active. And so people like some of those on the panel have worked to make hardware models that take that into account, in the very recent years, and so I would point you in that direction for your own work.
So I have a quick question. I'm actually thinking of doing this as a raise of hands to start off. So the conversation just now started moving towards, do we need to understand the whole brain or have a theory of brain function in order to do neural computation that makes it practical for applications? And it seems like that's a very high bar to set. So maybe I'll ask the question this way. Let's raise hands. Most of you are hardware folks. Do you think we have, raise your hand if you think we have enough information about neuroscience today. If NIH stopped funding neural research today, we had all the literature up to now, do we have enough knowledge today to get useful, commercially viable applications out of neural hardware? You can invest money in hardware development, sure, and algorithm development, sure, but no more neuroscience. So are we close enough on the neuroscience research side to make commercially viable neural applications? Who thinks so? Okay.
So I'm going to just jump right in on this one for a second. I definitely agree with it, mostly because I think a little bit of what I talked about actually was in that space of there's actually things we've actually built based on biological, things that we understand, at least what we've learned of the biology, getting it to various applications I would talk about, particularly word spotting and so forth, that directly come from this. Now, do I think that biology is probably stronger than this? Sure. But I think that alone already gives us applications that look like they are orders of magnitude better than what I could build commercially right now. So I think we already have a lot, and I think it's an interesting question because say neuroscience stopped, I hope it doesn't, but let's just say it did. I think we would, it's the same kind of thing of, let's say Moore's law stopped. Oh wait, it did. And, there would be a whole lot more to continue on. There's everything else that hasn't had the time to catch up, right? And we begin to understand that I think there's so much more possible that we just haven't caught up on. And if we did all these experiments, my sense is we would actually learn a lot about neuroscience. Then there'd be this whole set of questions to ask going forward. But it never works that way. Everybody's making progress, which is what you'd want.
So does anyone think the opposite?
Yeah, I see no evidence that there are really good commercially viable applications that we can build currently on what we understand from neuroscience. I think we've been trying for a long time. And the evidence, there are little point victories, and there's the current sort of deep belief fad. But it's not compelling. I don't find it compelling. I think we've still got to crack some fundamentals before we have neural-based applications which are commercially compelling in the way that, Mr. Turing's little ideas worked out quite well. We've got nothing close to that in the neural space.
Is your philosophy, if you build it, they will come? You're investing a lot in something that you don't see any applications for?
Well, the application for what I'm building is to understand the brain better, right? So we're very focused on the science. And I think I made this comment slightly glibly on the first day that if you look at sort of the European approach within the HPP project, it has a very strong science focus. if you look at the US brain program, it's much more application focused. I think applications are premature. We don't know how to do it. But if we build these large platforms, we may stumble across something commercially useful, but we can certainly pursue the science with them. But pursuing the science does mean continuing to pursue neuroscience alongside, right? Because we've got to get, I think we've got to get breakthroughs in the fundamentals, and I think theory is key to that. I mean, one sort of slight aside on this, which I was thinking a little bit earlier, is if we think the major communication in the brain is spikes, okay, so the gentleman to my right said we believe in spikes. We know spikes are not the whole story, okay? There are neuromodulators, there are these gap junctions, which are a very bad idea, but apparently they exist.
Close.
But if we think that information and flow in the brain is predominantly spikes, then AER tells us that basically with spikes all there is spatiotemporal patterns. So any component that can learn, recognize, and process spatiotemporal patterns is as good as any other. So I don't really care if it happens in dendrites or if it happens in point neurons. Any component that can do it is as good. We know that it doesn't matter whether we build our AND gates out of transistors or out of fluid logic. We have the same basic principles. And so I think spatiotemporal patterns and components that recognize, learn, and process them are where we should be looking. But where that leads, I have no idea.
So I want to go after this question a minute, because I would agree. I think going at the science is important, and I don't think anyone on this panel would disagree. Those questions are there. But I think there are starting to become some things that are commercial or things that have the chance to get there. And in terms of things that we have learned, I mean, I'll just take even some of the dendritic structures that have come out of the low-level understanding to try to create this kind of computation that, actually do look like they'll have some potential impact. At least they could. I mean, commercial world has a lot of interesting issues. We both understand that. A lot of people in this room understand that. But I think to say we don't have anything would be a problem, because then I think we'd be like, then I think that's just saying that some of the people who talked up here is like, oh, we're just ignoring that entirely. I think we've had some data points, but I think we need to go a lot further. I think there's so much more to go. I think that's a pretty easy call.
Right. So I guess the place that I see that neuroscience can make pretty big impact on society is that right at the interface of medicine and neuroscience, right? So, you think about the pain treatment that people are doing right now with epidural electrodes in the spinal cord. I mean, there's a whole bunch of control ideas that goes into how do you stimulate those those neurons, and what are the control loops, and so on and so forth, that gives us the ability to manage pain while moving around and so on, that if we did not understand neuroscience, we could not build these things, right? So then you think about prosthetics, or you think about the artificial or cochlea for that matter, right? I mean, how many people have been helped because of artificial cochleas? So I think there are, it's not all about computing. That's the bottom line, right? Computing is one aspect of what applied neuroscience is. Another aspect of applied neuroscience is what do you do about, helping humanity, making society better, and so on. Oh, and the science of learning. How do you take what we learn from neuroscience of learning and apply it to our classrooms and better teach our children, and so on. There's an entire massive area that the NSF invests a lot in the SBE, trying to address that point.
I would like to quote from an interview that Jan LeCun gave to IEEE Spectrum this week, or last week, which is quite strong, actually. We probably know that he doesn't like us at all. I actually talked to him quite a bit, and he thinks what we do is complete nonsense. And he makes this very clear here. He says we, neuromorphic people, are part of what he calls a cargo cult. You reproduce the appearance of a machine without understanding the principles behind the machine. You build radio stations out of straw. The cargo cult approach to aeronautics, that's an old thing, it's been repeated all the time, for actually building airplanes would be to copy birds very, very closely, feathers flapping wings and all the rest. And people did this back in the 19th century, but with very limited success. I mean, that is a typical criticism that is always being made. I mean, I'm being asked this question, and the flapping bird thing is one thing I hear all the time. Actually, I think it's not so bad. I mean, without birds, I think we would probably not even have thought of building airplanes. And also the principle of birds are very much reflected in airplanes. Of course, they don't flap wings, but I mean, birds don't flap wings all the time. If you see an eagle or a seagull flying slowly or really silently in the air, it just uses the concept of what is it called in English, dynamic buoyancy. Okay, and that's a principle which is also applied in airplanes. And feathers, for example, are necessary because to explain how an airplane flies is not so easy. And so turbulences, microscopic turbulences around the wings is a very, very important concept. And so it's represented in birds. So it's clear that by observing nature very closely, you can actually get hints to what the principles are. And then, of course, you reduce it to the necessary things and you build the airplanes. And so I think he's fundamentally wrong here by saying that copying nature doesn't lead anywhere. We may make mistakes, we may introduce things that are not necessary, but we have to try out. We have to be allowed to try it out. And we should not stop doing this because Jan LeCun tells us to do so.
And I'd like to see the plane that can land on a branch, by the way. You know, that's the plane I'd like to see, one that can land on a branch.
So or fly through the branches. Yeah, that's impressive. So I'll take respectful issue with Steve with your perspective about point neurons. Being in the computational neuroscience business, for me, very neural simulations, the rest of the computational neuroscience, well, much of the computational neuroscience field contents itself with point neurons. And I think the results thus far speak for themselves. One can mathematically show that a branch neuron with active branches can compute fundamentally more powerfully in certain definable respects than point neurons, regardless if you have a trillion point neurons. I have a paper in Neural Computation 2008 that outlines it. I mean, I could pose the setting in which it applies, but the point is that the computational neuroscience community prefers mathematical tractability, and up to its very leading members, many of them use point neuron systems, and not just lacking dendritic trees and nonlinear computation, but lacking many, many other active nonlinear elements that are ubiquitous everywhere in neural systems. The nature of synapses, the homeostatic regulation that a few people mentioned today, maybe most important of all, the wiring process and the self-organization of circuitry. And so computational neuroscience as a field, has had, and even more so today, has the opportunity to transition to a next paradigm that's more neural. The kinds of information that's being gathered now wasn't being gathered 10 years ago. And the computational power to simulate such complicated, intricate systems at scale, whether it's GPU computation or whether it's what Steve and Karl-Heinz have developed, that's now in our hands. And I mean, if we don't make the next 5 years a really golden time for computational neuroscience, then we've missed an opportunity that we'd regret, because the opportunity really does present itself now.
So I'm going to have to come back on this, right? I fully accept the evidence that these processes in dendritic trees are taking place in biology, and they are important for the biology, for how the biology works, and therefore they're important things that we do pursue in our modeling. But we need to keep mindful of the importance of abstraction. Okay, so the question is, how vital are they, and are they the only way to do something? Every transistor and every logic gate in my smartphone has interesting and complicated nonlinearities. It has, it depends on quantum mechanics. But if I try and understand my phone at the level of quantum mechanics, I'll completely miss the point, right? Because those transistors are organized in ways that support abstractions that mean you can ignore the nonlinearities and work at the next level of abstraction, and then you're much better placed to understand. And as I say, my instinct is that spatiotemporal patterns are the level of abstraction at which we should be thinking, and any component that can handle those is as good as any other. And it may not be quite how biology does it, but it may help us understand if we raise the level of abstraction a little bit when we think about the problem.
So I certainly concur in that the absolute reductionist to the molecular level of synapses, one can get lost there forever, and the same with transistors, and one has to grasp the appropriate level of abstraction in both electronic circuits and in neural circuits. I would just, two things. I would submit that the fact that pyramidal neurons, for example, have 100 to 200 functionally distinct regions that have 10,000 inputs scattered all over them. The inputs are not only themselves nonlinear and complex, but the 15 different ion channels that are embedded in the membrane that are activated by the inputs, that's not a system that can or should be reduced to a point neuron. And then second, and sort of complementary to this, I could point to results where that's been mathematically demonstrated. And so, yes, there should be appropriate primitives. For sure, one shouldn't unnecessarily dwell in the transistor molecular level details. I would just argue, and it's something that we're taking a lot of time on, and during this whole conference, I would just argue that when it comes to neurons, that there's a level of abstraction that is irreducible. It should be reduced as much as it can be, and Karl-Heinz and you both are overseeing a systematic process to reduce complicated models in a systematic way, which is, I think, a very good disciplined approach. And I think that what we'll find is that the irreducible level of neural structure is nonlinear dendritic trees rather than point neurons. But that's a great debate to have, and there's a systematic way to address it that you're both overseeing in your program.
Okay.
So I just want to add one more thing, because I think this debate's a really good conversation. I think there's also true in the abstraction, but I think there's one other point here that comes from the hardware itself. That's actually exactly what I care about when I'm doing, what I'm actually looking at in terms of application. If I were to actually say let me actually build the dendritic structure and look at how much complexity and power it takes versus taking the same thing of a set of point neurons, knowing that we've got that reasonably electrically modeled, and I look at the power dissipation, the case of the neurons is already going to be higher. That's very easy to demonstrate. It's probably a couple orders of magnitude higher to have a whole bunch of neurons and then deal with the routing versus dealing with an actual dendritic tree, whether they're be purely passive and I'm able to deal with in terms of the guiding of it, which is, it's very super simplification, or even in terms of the active channels in the structure itself. And you can kind of see this just in terms of the amount of capacitance charging up and down and how much power it's going to take. And so one of the things I think is really critical here, and I think I said it a couple of times, so I'll just making that the amount of power dissipated and the power efficiency of the modeling is so critical. And as soon as we go to do this in an application, it will be critical again. So it seems like it's one of those things that needs to be in the baseline of, if we don't know how else to call it, that's maybe at least the right way to kind of push through a particular theory.
What I really like about this discussion is that we have identified here an issue, something that cannot finally be answered today, is what is the computational role of structured neurons? What is it that you can do with point neurons, and which computational functions are arising when you have structured neurons where synapses connect at different distances from the soma? what I suggest is, I mean, we were going to continue this workshop, right? I mean, there will be another one next year. I know that there is a couple of workshops in HBP which are exactly dedicated to this question, structured neurons. They are all taking place in Paris at this new Institute of Theoretical Neuroscience. So you should look to their website. If you're interested in the topic, you can go there. I mean, we have very strong defenders of the structured neuron idea. Idan Tsegev is one of them. I mean, he really defends this very violently. And it's always very exciting. What we should do in the work, maybe next year, we could dedicate half a day, let's say half a day, inviting people that give us evidence. I mean, mathematically, simulation, maybe also hardware emulations. People like Jeff Hawkins could come again, and we could have a debate on that, which is then really also supported by evidence. That would be much nicer than just making claims.
Maybe just to kind of expand that a little bit more, tying that structured neuron discussion and sort of how far can we reduce computational primitives and what kind of functionality are we able to get out of them might be a sort of ongoing sub-theme to say, because again, to a certain level of abstraction, we might be able to do certain functions. If you need better power efficiency, energy efficiency, or some other metric, then you have to go to these more refined models or more detailed models. And I think that's, again, a trade-off maybe that can be highlighted further in the discussions. So I wanted to hand it over to Winfried. You had
Actually not, I'm looking at the watch.
Oh, okay. You do what?
Yeah, I've been waiting to ask this. I think bioinspired engineering is great. We've done that for centuries. But I really agree with the point of the need for underlying theory, because we build what we can compute. If you cannot produce engineer a product that has some particular function with bounded failure modes, how is this going to be commercially viable? So that's basically what I'd like to ask. Is there a prospect that we could use neuro-inspired computational devices and engineer them for a particular purpose?
But we're going into the realm of systems where where it is hard to get bounded failure nodes. Watson demonstrated that. Watson's not biologically inspired, at least at its roots, but it demonstrated itself, where it was very good at a large number of questions and failed miserably on a small number of questions. But yet it has utility, particularly when a human can be the final interpreter and arbiter. And by the way, I think this area in general, to me, it's the source of algorithms. And one thing I've observed is you need a collection of algorithms to solve a problem. You can't just have one algorithm to solve it. A student of mine spent 6 months participating in a self-driving car project, and the large number of algorithms that went into that is astounding. And I personally see that this community can be a source of a number of point algorithms that can help in parts of a engineered solution, not be the total solution itself. I do not see a self-driving car having triple spiking neurons in it. But I could see that being an algorithm that contributes to solving that particular problem amongst others.
So I guess a lot of these grand challenges that are posed to us by DARPA and other funding agencies do have very clear set of specs that you're trying to meet, right? So even though we are trying to implement them with neural or bio-inspired type of computation framework, we know when we're not meeting spec. So as long as they are bounded and as long as we have benchmarks that we're comparing our results against, and I guess I'm not seeing your point as far as not having clear failure modes.
Consider, say, a self-driving car. Okay, let's assume that you replace on the order of 100 million cars on the road with self-driving cars. Okay, what are the commercial and legal implications and all kinds of issues that you would run into with these self-driving cars?
So, I mean, that's a very deep legal issue. Fortunately, the standards they have to meet are not that high. They just have to be better than humans. And humans are pretty poor at that job, okay? Although the figures look fairly good, if you look at accidents per million miles, it's, you know, human drivers don't do that badly, but I think there is a clear spec. The driverless cars have to be better than humans.
So I want to go back to the question of where we are in the process, which is there's an interesting idea behind theory. So there, you know, like Newton basically came up with a theory, and then he said all these other things that you're seeing are outside of the theory, but they're explainable. Okay. In other words, there's friction. So maybe the big ball and the little ball fall at different speeds. Okay. So what the big question is in this area, is it, can we recognize a good theory when we see it? And we probably don't have the data to do that. Okay. We probably can't say, oh yeah, we don't care about the dendritic part of it because our theory doesn't need it. Okay. And it does all these things, but we don't have a clue why the dendritic pathways and activations and so forth behave as they do. Okay. That's not a good theory. The good theory says, here's our theory, okay, and all these other things you're seeing around it are explainable. They're explainable by things we don't fully understand, but we can say this is why they look like they look. So there is a big question, is when can you actually identify a good theory? That's actually a really cool question. So what I think Hawkins is trying to do, for example, is his idea is a good theory is a theory of intelligence, whatever that is. Okay. So he's got an idea about what a good theory is. Okay. And there are other people here who have other ideas about what a good theory is. Okay. And so the question is in this area, what makes for a good theory? I'm actually not an American type thinker. I'm sort of a European type thinker. I like that. But that's something to think. That's something to think about anyway.
Isn't it pretty well established what a good theory is? It is a good theory if it makes verifiable, correct predictions. That's the test.
I'm sorry, Newton did not make good verifiable predictions, except in certain circumstances.
Absolutely, he did.
No, I mean, so, I'm sorry. I'm not going to give you the example I just gave you.
The orbits of the planets is an excellent example of verifiable prediction. You can say this planet will be in 6 months, 12 days, and 13 minutes. There. That's a verifiable prediction.
And he had some that were not.
And of course, Newton was competing with other theories. So there were workable explanations for the motion of the stars and the planets. They were good theories. They did the job. It's just that they were very, very complicated. And what Newton did was he came up with a theory which was much simpler and as good at explaining the observations. Yeah. But you know, I think we're in the position in this space where any theory that allows us to do stuff, build stuff, is worth pursuing, which is why, as I say, you know, I don't want to sit here and say, you know, Elias Smith is right and Hawkins is wrong, or vice versa. I think they've both got theories which really allow us to make progress and see where they lead to. And I don't suspect that either of them is going to be the last word, right? I don't think either of them has got the theory of everything when it comes to explaining the brain. But they're extremely useful theories for making some progress. And then we see where we get to, and then we work out how we need to change the theory to make progress beyond that point. I mean, theory has, you know, Newton wasn't right, okay, because it took Einstein to make a few corrections. And I think we're at the early stages, we're at the beginnings of theories, but we just desperately need theories.
And agreed. And I'd say that when it comes to comparing the two different paradigms of neural computation that we've been debating, which is point neurons or nonlinear trees, there are theories of how nonlinear trees function, but there are also theories of how point neuron arrays function. And in order to really have the debate have some grounded test, one can and should do more of what's done extensively in machine learning, which is to create a benchmark challenge of an environment, with whether it's training and testing data or some other complex sensory environment, challenge the different parties in the field to build systems based on the type of primitives that they advocate, and then optimize them in a way that is sufficiently complete, and then see whether one has a distinctly more powerful capability. And then this would be, one definition of grounds to embrace the neural structure, the structure that's in biology, if it gives you that capability. There's very little of that in computational neuroscience, and I think it's high time that there's more.
Yeah, I was just going to make a couple of quick comments. I joined Bell Labs in 1982, and there were two things that were ground truth. One was that gallium arsenide was going to replace silicon. And the other, Hopfield came and gave a talk and told us that neural nets were going to be in the desktop PCs by the mid-1980s. And we know a lot about what happened to both of those predictions, even though in 1982 they were fairly broadly believed, at least in the environment I was in. And I think as a field there's been a long history of people believing that things were closer or that promises were more real than they've actually turned out to be. It's been interesting watching some of the presentations because there were some significant funders in the room. Knowing some of what's behind those significant funders, they don't think they're funding basic neuroscience research. They think they're funding applications that are going to be compelling within the next 3 to 5 years. And I have also started companies like Steve has, and I understand what 3 to 5 years means in terms of trying to get something into production. And I'm just curious what some of the individuals here think about meeting the objectives that the people behind these funders are giving them money to achieve.
I can give a concrete response to that, because one of the opportunities that's out there right now is the IARPA opportunity, and its challenge explicitly, and this is public and is in slides on his webpage. Its challenge is going to be object recognition in clutter, in background, in some incrementally increased levels of complexity and challenge, regardless of the sensory modality. So, can we do that and deliver in 3 to 5 years or less? Yes. The challenge should be, can we do that better than, or have a path that looks like we're going to be better than any machine learning system, classical machine learning system? And I think that's what they conjecture is possible, and that's why they're investing their time and effort to create the programs.
I see the same thing from the DARPA side, where I get funding. There are certain well-defined military problems that are not solvable today with the current algorithm sets. And part of the hope here is that these new emergent algorithms start generating solutions to those problems that at least can be demonstrated in a reasonable time span.
And tomorrow there is one that's closing in the BTO on chorioelectrics, which is how neuromodulation can help diseases. And I think that's, fabulous, right? It is a great example of, trying to understand neuroscience and then trying to, use it as the pill, if you will, to deal with the disease as opposed to, taking drugs. I think it's an excellent idea.
I'll go the opposite and say, when DARPA, let's say, funded ARPANET, how the internet today, based on what they wanted to use it for, is totally different. So I don't think it's necessary that they have these challenges, which is exactly what it needs to do, is building the technology that, they will find other uses elsewhere. We never know. I think some of it might be many years down the road outside the program that the true benefits of these kind of programs will show up. So I don't think we should just look at what are the metrics that's given by these programs as the final and be-all goal. It's an intermediate step to show applicability and all that kind of jazz.
So actually, this is probably a good time to wrap up the discussion. So please, let's thank the speakers and the panel again. And we'll convene again tomorrow at 8 a.m.